Hello everyone. In this simulation, let us consider an electromagnetic wave in free space. But before diving into the simulation, let us look at an example. Let us look at this equation. Y is a function of x comma t, 5.24 cos 13x plus 57t plus 4.25. So such a equation represents a wave moving in the x direction and the displacement is happening in the y direction. Hence the wave is moving in xy plane. It has an amplitude of 5.24. If y is in centimeters, 5.24 centimeters. Wavelength is 0.48 meters because 13 is equal to 2 pi by lambda. Frequency is 9.07 per second because this is 2 pi by t. So 2 pi by capital T is 57. Hence frequency 1 by t is 9.07 per second. And this is initial phase 4.25 radians. Now, how does an electromagnetic wave look? So typically these are the equations which we see in textbooks. E for electric field is a vector, is a function of r is the position vector and t, the time. So it is E0 cos k dot r plus minus omega t plus phi. So E0, the amplitude itself is a vector, and in any given situation either it is plus or minus. As a consequence of Maxwell's equation, there's an associated magnetic field also. It looks identical. The initial phase is same, angular frequency in time is same, spatial frequency is same. It differs in the amplitude term. It's a different vector. So such a set of equations represents an electromagnetic wave moving in the k direction and absorbed at point r. But for today's simulation, let us keep things simple. Let us consider an electromagnetic wave moving in free space in the z direction and absorbed along the z. Hence what happens is k dot r becomes kz. So equation simplifies to E0 cos kz minus omega t, and B is B0 cos kz minus omega t. Generally, this minus sign indicates a wave moving in the positive z direction. So initial phase, because it is same for both of them, so I have excluded it. So what we will be visualizing today. So the amplitude term is a vector. Point number 2, both the vectors E and B are perpendicular to each other. Magnitude of B is very small compared to E. That is, E by B is in fact c, the speed of light. The three vectors, the propagation vector, electric field vector, and the magnetic field vector forms a triad, a right-handed system. We'll also visualize the magnitudes of omega and k, and also measure the speed as c. So let us look into the simulation part. As there are three directions x, y, z, let us familiarize ourselves with the axis system. So this will be the axis system where the visualization will be done. This is x direction, this is y axis, and this is z axis. And we'll be looking at the electric field and magnetic field along this line. And to help our eyes visualization simple, I have put two vertical lines, they will guide the eye. And origin is somewhere here, the origin of our axis system. Now before going ahead, let me clarify that we are not looking at the source of the electromagnetic wave. Some wave has been created and we are observing it in the space somewhere. So we are not presently bothered about the source. That will be aspect which will be dealt in another video. So let us see the simulation first. So here it is a running time, the time in omega t. Now as we can see, the blue one is the electric field. It is oscillating in the YZ plane, and the red one is the magnetic field. It is oscillating in the XZ plane. And the wave itself is moving in the Z direction. Now this plane over here is the XY plane, and we see the dashed lines. So these dashed lines represents the electric and magnetic field vectors at this point. To make the visualization simple, I have put those separately in this axis system. This is X and this is Y. So the blue arrow is for the electric field vector at this point and at this time. And red dashed line, which is over here, has come here. It is the magnetic field vector at this time and at this position. So we can see that electric field and magnetic field are oscillating perpendicular to each other, and they are also perpendicular to the direction of propagation. So another thing which we can see is the magnetic field is smaller compared to the electric field. In fact, the factor is very high, E by B is equal to C. Here, for the sake of visualization, I have put a small number, maybe about 20 or 25% of the electric field. Also, for this axis system, the positive X is this one, positive Y is this one, and positive Z is coming out of the computer's plane. Now, let us look at each parameter one by one. Let us look at the wavelength. Or let us put a number of 1000 nanometers. And this is, let us put in the X direction. So we want electromagnetic wave of 1000 nanometer oscillating electric field in the X direction, XZ direction. Let us see. Now the electric field is in the horizontal plane, that is XZ plane, and it is moving in the Z direction. Now look at the numbers. The Z axis is going from 0 to 3 into 10 power minus 6 meter, that is 3 microns. So within the 3 microns, it is 1, 2, and 3 for the electric field. For the magnetic field, 1, 2, and 3. So for 3 microns divided by 3 is 1 micron. So hence wavelength is 1 micron or 1000 nanometers. Another thing which we can see is they're in phase. So at this time and at this position, it is at its maximum, and electric field is also at its maximum. Now, how do we look at frequency? Remember, for wavelength, we need to look at spatial points, and for frequency, we should observe at one point as a function of time. So we'll take this itself, which is in this plane, and see how this electric field vector changes. Rather, how many times it changes in a particular amount of time. So let us see that. 1, 2, 3. So the electric field has changed 3 times in a time of 10 femtoseconds. So the time period will be 10 by 3 femtoseconds, and the frequency will be inverse of that. So let us now look at the numbers. So the equation will consist of amplitude and the cosine part. First, let us look at the cosine part. Cos 0.628 into 10 power 7 x minus 1.885 into 10 power 15 t. So for the clarity, I have removed the 10 powers. Actually, the numbers are here. So this is the value of k, and this is the value of omega. So you can verify that if the time period is 10 by 3 femtoseconds, the frequency would be 1.8 into 10 power 15 radians per second. Also for wavelength, you can check it out. Now let us look at the same thing in the other plane. So as you can see, the cosine time did not change, only the amplitude term changed. So this is a vector. Earlier it was I, now it has become J. So it's the same thing, but the electric field is in the vertical plane, magnetic field is in the horizontal plane. So we can see that now the amplitude term is itself a vector. K and omega are, the magnitude is very high. Omega is of the order of 10 power 15 radian per second, and K is of the order of 10 power 7 radians per meter. Now let us change the wavelength. and let us keep the angle same and observe the rate of change of the electric and magnetic field vectors. Now you can clearly see the electric and magnetic field vectors are oscillating faster compared to the earlier simulation, and you can see the frequency has also increased. So is the wave number. So here the wavelength has decreased, so we can see more number of waves per unit length, hence k is also increased, and it is faster, hence the omega has also increased. Let us put some other number, that's 200 nanometers. Now it is much faster, you can see. So to summarize, in an electromagnetic field, there's electric and magnetic field. Both of them oscillate perpendicular to each other in free space and perpendicular to the direction of propagation also. The amplitude term is a vector. The k and omega are of the order of 10 power 7 per meter and 10 power 15 per second. Hope you have enjoyed this simulation.